Hello everyone, welcome to another video. In this video we are going over the implementation of SHA-512 in Python. This video is not an in-depth explanation of SHA-512, so going forward I assume you have some familiarity with SHA-512. However, if you would like to know more about SHA-512, there are two other videos in the channel that explores SHA-512, how the algorithm works, what mathematical tools we need to understand the algorithm, and a detailed example. So actually in this video, we are going over the same example, and we're just gonna implement it in Python. Here we can see a quick overview what we are going to see today. As much as I wish to not import libraries or use additional libraries, because in general I would prefer to keep everything self-contained, we need a few libraries in order to make our lives a little bit easier. So we're going to go over that in the first part, and then we have the pre-processing that is needed for SHA-512 because the input has to be of a certain type, and then we're gonna go over the initialization of the initial vector and constant we use, including prime numbers in SHA-512. Then we need to create the logical functions that are required in SHA-512. First, we're going to go over the building blocks of those logical functions, and then we put them together to make more complicated logical functions. And then in the last part, we put everything together, and we're going to go over the main algorithm, and then we're going to get a message digest at the end and compare it to what we were expecting to get. And just to let you know, this is not an efficient implementation of SHA-512, and as we will see at the end of the video, there are other methods in Python that one can use to get the message digest. So the main purpose of this video is educational, and it is not to be taken for your own implementation of SHA-512 that you need to use. That's not the case. This is an educational video, and I would actually be happy to know if you would approach it in a different way. I'm sure many components that I'm gonna go over can be done in different way, maybe more efficiently. So for sure, please do let me know in the comment section. And yeah, it would be good to see other ideas. And without further ado, we can get started with the implementation of SHA-512 in Python. So as we said, we need to import a few libraries in Python to make our lives easier. So first of all, we need the MP math library, and we are going to import everything from it. So this star implies that all the functions will be imported. And MP-math is a library in Python that deals with real and complex floating point arithmetic with arbitrary precision. This will be useful when we deal with prime numbers later on. We also need the SymPy package, and we will see how it will become useful. But in general, the SymPy package is a Python library for symbolic mathematics and also number theory. Also, from the SymPy package, there is a function that we can just import right here. Here we get our first error, and because this was to be SymPy, this works well. we need this last line, and we'll see later, but we need it to solve linear congruence relations in Python for the SHA-512 algorithm, as we will see. Now, for the pre-processing, as mentioned, SHA-512 requires the input to be a string binary bit, so a string made of 0 and 1s, and it has to be a multiple of 1024. So the pre-processing part makes sure that the input satisfies those criteria. And we are gonna follow these bullet points one by one. So we see that first of all we need to have a message, and as I mentioned, we are gonna go over the same example that I've gone over in a separate video. However, this time it's just being implemented in Python. So if you'd like to familiarize yourself, feel free to have a look at that video. So the message that we're going to use is simply a very small example, actually, ABC. And we need to encode these. So for the example that we choose, we use the 8-bit ASCII encoding. So we can get the ASCII value of a letter in Python, actually. Well, for example, for letter A, the ASCII value is 97. We can make this into binary. We can find its binary representation. So simply if I do OR 90A, it will give me the binary representation of 97. And then we can make this look a little bit nicer by getting rid of the first two characters. It's just a Pythonic way of the input. So I mean the output that we get. So to make it more nicer, we can get rid of the first two characters. And because we want the 8-bit character encoding, we can so right now we have 7 bits, but we want 8, so we can just make sure that it's gonna be 8 bits by this command in Python. Next, we can speed things up a little bit by using list comprehension. So I'm gonna create a new variable. You're gonna see a lot of variables throughout the video, and I must admit that not all the names are chosen very creatively, so I apologize if the names don't sit well, but I hope it will help us to get the message at the end, the message digest. So here, as we've seen, we are just making the output look nicer, and then this will make sure that we get 8-bit representation. And then here we use, this is the I that we use, which is our iterable variable for I in the message. And I'm just gonna display the message bit to make sure that we have everything we need. So basically, and lastly, we need to concatenate all of these values. So message bits concatenate, and we can use the following command in Python to get that. And we're gonna display the message. So basically, where in the pre-processing it says let m denote the message, this is the message. The message has to be a string of bits of 0 and 1. The next bullet point says let L denote the length of the message. So that's actually very easy. It should give us 24 because we have 3 characters, each 8 bit long, so 3 times 8 is going to be 24 as expected. And then the next bullet point says append 1 to the message. So we are gonna do that right now. Concatenate 1, because we're adding 1 to it, which can be done very easily by just simply concatenating the message that we made so far with 1, displaying everything. So yeah, as you can see, yeah, we have an extra 1 here compared to this one. So far so good. Now the next part says add k0 to the end of the message where k is the smallest non-negative solution to this equation that we see here. So we need to solve the congruence equation L plus 1 plus k is equal to 896 mod 1024. So we need to change things a little bit so that we can work with it in Python. So as I mentioned, SymPy library is the library that we need to use in this case. SymPy library provides a Diophantine function to solve congruence equations. So in general, a congruence equation can be written in this form, and then we can change it, transform it into a Diophantine equation, which is in this form. However, SymPy itself requires a bit of rearrangement to make this work. According to the documentation, this is the equation that the Diophantine function will try to solve. So in this particular example that we are trying to solve, the value of a is simply 1, so we don't even need to introduce that. X is what we're trying to solve, particularly we are trying to solve k. B is this value, which is 1024, and C, which is this value, is simply 896, and we are not interested in the value of m, which is this variable here. So let's see how it's done in Python. So as I said, SymPy allows us to do symbolic manipulation and calculation in Python. So first we need to define that these are symbols. I try to keep the namings consistent, and we have to make sure that these are integers. Next, we are gonna define the variables as we've seen here. So we have 1 plus L plus K, B is equal to 1024, and C is equal to 896. Now we can simply use the Diophantine function in Python off of the SymPy library. Diophantine, and this is how we're gonna give our parameters. So we have x plus b times m, b times m minus c. So this is the equation that the Diophantine function in SymPy library is trying to solve, and this is the output that we get. So we get two variables here. So this is one, and this is the second one. This second one, which is just t0, t subscript 0, is the m that we defined earlier. So we are not really interested in that. We are more interested in this part, which has the information that we are looking for. But again, to extract that information, and I'm just gonna, we know the answer based on the other example that we've seen in the other video. It should be 871, but to give you a generic approach that you can use in the future for any other similar problem, this is the way that we can go ahead. So first of all, we notice that the output that we have is a set. It's not a list, and set in Python is not iterable, so we can actually transform the set into a list very easily in Python. So this would give us a list. So now I can iterate through the values that I have. And as I said, I'm interested in the first entry of this list. So I can access that element in the following way. Now, I can also get the different parameters that I have here. So we have 1024 T0 plus 871. So let's actually save this as another variable called solution, SOL for short. If I look at the arguments of this variable, we see that we get the two coefficients, 871 and 1024 times T0. But I am only interested in this value, 871. So if I look at sol args 0, which gives me the first output, is gonna be 871. And in general, in this particular example, this is already the smallest positive integer that we are looking for, but in general, if we wanted to make sure of that, this is how we can ensure that that's what we're looking for. Now, going forward, it's better to keep things consistent. So we are going to be dealing with a lot of integers in Python, so it's better to just have all of our integer as Pythonic integers rather than any other integer. And I'll just tell you what I mean right now. So if we inquire the type of the output that we have, we see that it's an integer off of the SymPy library, but we can easily change it into a Pythonic integer by the following built-in function in Python. So now this is a Pythonic integer, and we can make sure of that easily. We just put in into the type command. We see that it's an integer within Python, which is what we wanted. So now that we got our value, we see later on that it says add k zeros to the end of the message. So I'm just gonna call a new variable zero pad. Making sure everything is working fine as expected. And then the next bullet point says, then append the padded message that we have so far with the 128-bit binary representation of L. So again, we can do that easily as well. We can find the L in the binary format, binary, and we need to make sure that things look nice here. L binary, and to make sure that this is 128-bit, we're just gonna use this command, and there we go. There we have it. This is the 128-bit binary representation of L. And for example, because we need to add these many zeros to our concatenate message that we had so far, we can create multiple instances of a simple string by simply multiplying it by a number. So if I have the 0 string and I want 2 copies of it I just multiply by 2. Now we can put everything together and create our padded message. So message, we can create a new variable called message padded, which is equal to the concatenated message with one that we created earlier, and then we're gonna add k zeros as we've seen so far, 0 pad, and then finally we can concatenate it with the 120-bit binary representation of L. And put everything together and see the output. So this is our output. That's the message that is gonna enter in the SHA-512 algorithm. So this is our input, and as we see in the description here, it says at this point the length of the padded message must be a multiple of 1024. So just a quick sanity check. In this case, it's just one block, so it is actually gonna be just 1024 bit. And as a sanity check, we can inquire the length of this variable, and it should be 1024 as we were expecting. Next, we need to deal with initial vector and constant that are used in the SHA-512 algorithm, and specifically prime numbers. So there are two different places where prime numbers appear in the algorithm. One, we need the first 64 bits of the fractional part of the square roots of the first 8 primes, and these define our initial hash values, which we see them listed here. And then later on at another point of the algorithm, there is a nested for loop in which we see this vector k with 80 entries, and this is a vector actually consisting of the first 64 bits of the fractional parts of the cube root, actually, instead of the square root compared to the last part that we saw, of the first 80 primes this time. So we need the first 8 primes for this section, and then we need the first 80 primes. And here we need to deal with the square roots, and here we need to deal with cube roots. So we see how we can compute these values in Python. So I've already imported everything, all the functions from the npmat library. So the following is actually from the npmat. This will show us the precision. So right now, this argument that we see here, np.dps, DPS stands for digits displayed, if I'm not mistaken. So at the moment, only 15 digits are displayed. So for example, if I look at the square root of 2, I think it means that 15 digits are displayed. However, we can increase the amount of digits that are being displayed by simply changing the value of np.dps, and we can do that simply like this, and we set it to 50 just to make sure we have enough digits to work with. This is actually very important in calculating the first 64 bits of the fractional part of the numbers that we are dealing with, because if you do not have enough digits in the decimal point, then it doesn't give you the result that you're looking for. So now if I look at the square root of 2 once again, we see that we get a lot more decimals after printing the value for square root of 2. Now, if I want to get the fractional part of a number, I can do that very easily again using the NP-Math library. So this is just a fractional part. So fractional part is simply just drop, if you're dealing with a positive number, just drop the integer part. So if it's 1.41, for example, we get 0.41, and so on and so forth. And then because it says the 64 bits of the fractional part, we need to multiply the number by 2 to the 64. So it's good to know this value. And then we can do everything within the NP-Math library. So multiplication, actually one way to multiply numbers in general in Python is just simply like use the star, but you can also use the functions within the NP-Math library like this. So it just takes 2 arguments and then it will give us the same value, but it's done with the NP-Math library. So in our specific case, we are interested in the multiplication of the fractional part of square root of 2 and 2 to the 64. And that's the value that we get. Now, we are interested in the integer part of this value, and to get the hexadecimal we can use the built-in hexadecimal function in Python. And again, just to make things look nicer, we can easily do that by dropping the first 2 characters in the string that we get. So we get this value as our hexadecimal representation of the 64-bit of the fractional part, the square root of 2. That was a mouthful, and we can see this value is, starts with 6a and ends with 08. So let's see if it matches those values. Yeah, starts with 6a, ends with 08, and you can go through the remaining values and compare and make sure that it's actually what we were expecting. So that deals with that part. Now, how do we go about finding the primes? Maybe finding the first A prime is not that difficult. You can just create a list and add them just by knowing the primes, but we also need the first 80 primes, and I don't think there are that many people that know the first 80 primes on top of their head, so we need a systematic way of approaching this problem. So again, we can make use of the SymPy library in Python, use the sieve method off of it. So this command will give me the first prime. And so for example, if I'm looking for the second prime, just pass it 2. Now I can simply get the first 8 primes by the following command, 1 to 9, and that will give me the first 8 primes, which is what I know, what I wanted. So I can save them in a variable, first 8 primes. There we go. And now I can create a function that simply computes the 64 bits of the fractional part of the square root of a number. So this is the function I'm creating. And I will store the value as a hexadecimal value at the end. So we're gonna return. So we can just simply this, copy it in here, and now the only thing I need to change is that I'm passing n, so it has to be dependent on n, not just like a constant. So that's what I'm gonna change, making sure everything looks good. So if I look at the square root, I should say the 64-bit of the fractional part of, like, let's say 3. This is what I get. So let's see, starts with BB and with 73B. Let's go back up, and yeah, that's what we were expecting for 3, and so it's doing the right thing. We can put everything together for the first 8 times. Binary fraction of the 8 primes using the least comprehension again. First 8 primes. Just print them, displaying them, making sure everything looks good. So that does that for that part, and then we can use the similar process for the first 80 primes. So we can go a little bit faster here. So first, actually 80 primes, we can find them the following way. This is actually rather, this computation is done rather fast in Python because we are only interested in the first 80 primes, but if you're looking for hundreds or thousands of primes, maybe this is not the best method. But the whole point is that these calculations should be done fast on a computer, so hopefully there are built-in packages and libraries in your language of choice, if it's not Python, that do the same calculations. Just gonna display the first 80 primes, making sure everything looks good. And we can just simply define the same function that we did for square root, but this time for a cube root. Roots 64 bits x, and again passing n. I can simply copy paste this, but this time with the minor change. So here we're taking the square root and we have to change it to a cube root, and actually there is another command in the npmath library that does that, which is the cdrt for cube root, just to make sure that it returns something meaningful at least. Which is what we were, well, I'm not sure if this is the right value. Hopefully we'll see at the end of the video that everything's come together, that this is the right value. I don't have the actual value in front of me right now, but hopefully this is the right value. But it does return something meaningful, so that's the good news. And then we can, again, use the least comprehension approach, store them in a list. I'm not gonna display this because it's a long list of 80 primes. Actually, I should say the 64-bit fractional part of the cube root of the first 80 primes. So hopefully it's doing the right thing. Now at this point we are moving to another part of the SHA-512 implementation, which is the logical functions that we need to use. So just to remind ourselves, there are building blocks that we need, and then we're gonna use these building blocks to create more complicated logical functions. So first we have the XOR operator, the AND, the bitwise complement, right shift, and right rotation by n bits, let's say. So let's first go over the bitwise complement implementation in Python. Again, just to remind ourselves, if we have a bit 0, the bitwise complement will turn it to a 1, and similarly if it's 1, change it to 0, and here we see a quick example. I'm just gonna define a function here, bitwise complement, and we're gonna return the following value. So this is off of the string built-in library in Python. So we have to make use of the translate and then the make trans. So translate returns a copy of the string in which all the characters have been translated using a certain table. So now we're gonna define the table by the following method. So what this is doing is that it says, if you see a 0 in the string, change it to a 1. If you see a 1 in the string, change it to a 0. So that's the table that the translate method looks up to see how it can do the translation. So this might be new to you if you haven't seen it. It's not something that comes up frequently in Python. If you knew another approach of achieving the bitwise complement, please let me know. So to see how, that it's doing the right thing, let's define a string like 0, 1, 1, 0, 0, 0, 0 as an example. And I want to see what is the bitwise complement of this string. Well, we know that it should give us 1 everywhere we see 0 and 0 everywhere we see to give us 0 wherever we see 1. And yes, it's doing the right thing, and the bitwise complement of this string is the following string that we see here. So we can gain confidence in this function. Next, we need the AND operator. Again, just to remind ourselves, AND operator only returns 1 when both of the bits are 1. In any other case, it returns 0. There is actually a built-in function in Python that does this, which is just simply the AND symbol, and we'll see how it works. It might not be intuitive if you haven't seen it before, but yeah, you see that we get 2. So the question is, how is that 10 and 3 would give us 2? But if we dive a little bit deeper, it makes a lot more sense. So if I look at the binary representation of 10, this is what I get. And if I look at the binary representation of 3, this is what I get. Now, to make things a little bit look nicer, I'm gonna just make sure that it returns a 4-bit string. So right now we can see that if you compare these two outputs, the only place that both of the bits are 1 is in the second place from the right, and everywhere else it should be 0. If I look at the binary representation of 2, and again just to make sure that it's 4-bit long, the output, we see that it matches with that. So the AND operator, it's a built-in method in Python that does what we want. It's just that the output may not look very intuitive in the first glance. Also, it's good to know that we can change, we can go from a string like this and get back its integer representation in base 10. So if I have this string of bits of 0 and 1, I pass in 2 to specify that this number is in base 2, and I'm interested in this number, the value of this number in base 10, so that's what I get. Next, we have the bitwise XOR operator. Just to remind ourselves, this is an operator that returns 1 whenever only one of the bits is 1. In any other case, it will return a 0. Again, there is another built-in function in operator in Python that does that for us. Usually in mathematical software systems, this is the symbol that we use to exponentiate numbers, but in Python, to exponentiate a number, we use double star. So for example, 2 to the power of 3, which is 8, needs 2 double star. So the question is, what does this operator do? This is actually the XOR operator. So if I do this for 2 and 3, I'm getting 1. Again, this may not be intuitive if you haven't seen it before, but again, if we just look at the binary representation, I try to do it a little bit faster this time around since we've already seen one example. And yeah, there we go. So we see that the binary representation of 2 is 1 and 0, binary representation of 3 is 1 and 1. If you XOR these two values, you would only end up with 1 in the very first position to the right, and that's the binary representation of 1. So look at that. We see that this is the binary representation of 1. So we can be sure that this is doing the right thing for the XOR operation. Next, we have the right shift operation. As a reminder, the right shift function, the way that we can think of it is that if we look at the rightmost bit and we want to right shift it by 1 bit, it will cause it to fall. So for example, if this is the starting string 0 0 1 1 0 1, and if I want to right shift it by 1 bit, that 1 will fall, and then we add a 0 to the left, and that's how it's done. So if we keep doing the process, eventually all the bits are gonna fall, and we end up with 0 everywhere. Again, the question is, how can we do this in Python in a systematic way? Again, good news is that there's another built-in function, and it's done using the greater than symbol twice. So if I want to right shift 25 by 2 bits, this is how I can do it. Again, this is your first time, might not be that obvious, but let's have a look at the binary representation of 25. So we see that this is what we get. And let's look at the binary representation of 25 right shifted by 2 bits. So yeah, if we remove these 2 bits, this is what we get. Now you might notice that here when I apply the right shift operation, I always end up with the same number of bits, but not in this case in Python. The reason why I tend to keep the same amount of bits is that we will see very soon that in the SHA-512 algorithm, when we apply these logical functions, the sizes of the input and the output is the same. All the operations are done over 64-bit strings, so the input is 64-bit and the output is 64-bit. So it's important to make sure that at the end we're gonna end up with the same number of bits for our output. So this is just a reminder that we need to make sure of that as we're gonna implement the SHA-512 in Python. Now the last building block that we need to remind ourselves of is the right rotation. And right rotation is very similar to right shift, except that once the bit falls, it actually makes a circular movement and goes to the very left of the string. So for example, if my starting bit string is 001101 and I'm shifting it by 1 bit to the right, I simply shift that one, the rightmost one, to the left, and then shift every other bit 1 to the right. And then in this table you can see how it looks after right rotating by 3 bits. For this one, I'm just going to define a function called right rotation s, which is our string, and n is the number of bits that I would like to rotate. I'm just gonna update the value of n within this function. This is actually not necessary for the purposes of SHA-512 algorithm, but this is a good practice to have in general, and I will explain why it might be useful. And this is how we can actually achieve the right shift in Python. So that's the function that we need. So again, reminding ourselves the string that we defined earlier. If I want to right rotate this by 2 bits, so this if we keep track of these 2 bits, we'll see how it would look after shifting it by 2 bits. So everything has shifted by 2 bits. I can move this 3 more bits, and then this one will come to the very left. So let's just do that. So yeah, you can see if I shift everything, the initial string by 5 bits, this one comes to the very left. Now, why did I add this second line here? So if, for example, you were to right rotate the string by, let's say, 9 bits instead of 2 bits, and keep in mind that the length of our string is 7, so it has the same effect. Right rotating by 9 bits has the same effect as right rotating by 2 bits. So this line ensures that we can achieve this without encountering any error. And as you can see, these 2 outputs are the same. Now that we have gone over the building blocks of the logical functions, we can put them together and create more complicated logical functions that are needed in SHA-512. So again, as a reminder, these are the functions that are used, the logical functions that are used in SHA-512. The input of all of these functions is a 64-bit word, and the output is also another 64-bit word. So that is something important that we have to make sure when we are implementing it in the computer. because, for example, if we use the AND operator in Python, it drops the number of bits, or if you're doing the right shift, for example, they could possibly make your string to lose some bits. So you need to make sure that at the end of the day you end up with a 64-bit word, and we are gonna see how that's gonna be done. So the first function is the ch function, or the choose function. We have 3 inputs, x, y, and z, and the way that we are gonna define and work with these variables is that we expect that our input is already a string, not necessarily 64-bit, so that's why we have to maybe ensure that they are 64-bit. So first I am gonna make sure that x is a 64-bit string. I only do it for x, as we will see later on, because we are applying the bitwise complement, but it's not necessary to do for y and z, as we'll see shortly. So I'm gonna get the integer representation of x in base 10. Same thing for y and z. Now I have to apply the AND operator. So the reason why that I change them to integer format is that I'm using the AND operator, and in Python, to use the AND operator, it's easier to be in integers base 10. And that's simply what we get. And we can do that. So this will give us x and y, and next I have to compute complement of x with an AND operator on that value with z. So let's do that. So right now we know for a fact that x is a 64-bit word, which is what we want. So we compute this value and we take its AND operation with z, which we've already defined as s3 here in the integer format. And then lastly, I can get the XOR of these two values by the operation that we've seen before. And I need to make sure that the final output is going to be in binary. And again, importantly, I have to make sure that the output is 64 bits. Just to see an example, if I have 1, 0, and 0, this is the output I get. Why? Because, well, the x and y is gonna be 0, and then the bitwise complement of 1, which is just 0, use the AND operator on it with, again, 0, it's just gonna be 0. So this is not that interesting. If we want something that doesn't return 0, we can try this string, these strings, and we see that this actually gives us 1 simply because 1 and 1 will give us 1, and then 1 and 0 will give us 0. You bitwise take the XOR of those two arguments and you end up with this string. The next function that we need to define is the major MAJ function, or major. or sorry, the majority function, I must say. I think that's what it's called. I might be wrong. If you know that there is another name for it, please let me know. I'm curious to know for sure. So again, we are gonna pass in the arguments. Again, let's remind ourselves of the definition. We have to take the AND operator among all the 3 inputs and then finally XOR all of them. So S12. And then lastly, I'm gonna take the XOR between them. And I'm just gonna return this value in a string of 64 bits, which is the important part. So let's see some examples. Majority function on 1 0 0. So this returns 0. So let's go over it and see why this is 0. So if we look at it, we see that x and y, because x is 1, so this will return 0. Z is 0, so this will return 0. So sorry, this one returns 0 because y was 0. This one returns 0 because z is 0. And this is going to return 0 because both y and z are 0. You XOR all of them, simply get 0. And again, if you look at the same example, we see that the same example that we saw for the case of the choose function, we see that again it returns 1. Again, x and y are the only things that are 1, so the AND operator will give us 1. Every other case it will return 0. You XOR all of them and you end up with 1. Now we have to define the sigma function, capital sigma I must say. X, again, making sure that the input is 64-bit long, that's important. Now let's look at the definition. So we have to right rotate the input by 28 bits, 34-bit, and 39-bit, and then take the XOR of all of them. So let's just do that right now. Right rotation of x 28. Again, I'm converting them to integers because I have to take the XOR in the using the built-in methods in Python. And 34 bits, and lastly 39 bits. And then this is gonna be our output, S1, XOR S2, XOR S3. Making sure that the output is 64-bit long. And to see if it's implement it correctly, we just gonna see a quick example, and this is what we get. And you can go over this and ensure that this is convince yourself that this is the right output. Just to give you a quick hint, if I were to take a look at this, the length of this string, it should be 28, as we expected, which is great. Now I have to define sigma 1. So for the most part, we can use the same function that we defined for sigma 0 with minor adjustments. So let me just rename this to sigma 1. Going back to the definition, I need to right rotate by 14, 18, and 41 bits. So let's go ahead and make those changes. 14, 18, and 41 bits. And let's look at an example. And again, you can convince yourself that this is correct. If we look at these, the length of this string, it should give us 14, hopefully, which it does. Now, next we have sigma 0, lower sigma 0 actually. So let's go ahead and define that. Sigma 0. So again, I have to make sure that the input is 64 bits. Now let's look at the definition of sigma 0. We have right rotation by 1 and 8 bit, and then right shift by 7 bits. This will ensure that we are shifting everything to the right by 7 bits. And then finally I have to take the XOR of all these values. And making sure that the output is 64-bit long. Making sure that it's doing the right thing. Let's look at a quick example. So at least the output is doing something sensible. Now if it's the correct value or not, you can convince yourself that hopefully this output is correct and it's what it should have been produced. And lastly, we need to define lower sigma 1. It's very similar to sigma 0. Let's look at the definition again very quickly. Right rotation by 19 bits, 61 bits, and right shift by 6 bits, and then finally taking the XOR of all those values. So I'm just gonna go ahead and do that. 19 bits. Oh, we have to make sure that we're not making changes to the wrong function. So this should have been untouched actually. This is the one that we need to make changes to. 19 right rotation by 19 bits, right rotation by 61 bits, and then right shift by 6 bits. hopefully this should give us the correct output. And you can see a quick example, and I will leave it up to you to convince yourself that this is the correct value. Now we have all the ingredients that we need to actually use them for the SHA-512 algorithm. So let's quickly remind ourselves what the algorithm is asking us to do. So we need to go through n blocks. In our particular example, n is already 1, so we only need to go through this for loop once. So in the first step, we need to prepare this message schedule. Then we need to initialize the 8 working variables, A all the way through H. And then we have an inner for loop that goes through 80 iterations. And here we update the 8 working variables. And at the end, we're gonna compute the intermediate hash values. We're gonna update those hash values. So let's go through them step by step. So in the first step, we need to prepare the message schedule. So let's see how that is done and how it's defined. So we see that it says first divide the ith block message, I should say. So in our case, we only have one message block, and we are going to divide it to chunks of 64-bit words. So this will create 16 message blocks that are labeled from 0 to 15. And then from the 16 to 79th iteration, we have to use this definition to build the remaining parts of the message schedule. So let's do the first part first, dividing the message to chunks of 64 bits. This can be done easily in Python, again using this comprehension, reminding ourselves the message that we are working with right now. This is the message that we had. So we use that information, and using this comprehension approach, we have a variable I, and we want to divide it into chunks of 64 bits word. And we're gonna go from the first place of the message to the whole length of the message in chunks of 64 at a time. And we put everything together, and that's what we get. So you can see that it at least kind of looks good, because the first 64 bits, we can see it here. You can compare it with this these bits here, and then we see that at the end we have these bits here, which is comparable with these bits right here. So it looks like it's doing the right thing. Now we have the first 16 part. We need to create the remaining parts of the message schedule. And just as a sanity check, just to make sure that we have 16 elements already. Yep, we do. And we can create another function to actually compute the next part of the message schedule. So we apply this lower sigma 1 and lower sigma 0 to wt minus 2 and wt minus 15. And then also keep in mind that the SHA-512 algorithm states that wherever we see addition, the addition is done over mod 2 to the 64. So that's something that we have to be mindful. So it's good to keep everything in a base 10. So when we add the summation, we just simply compute its value mod 2 to the 64. So let's put everything together. Lower sigma 1. W minus 2 get this value in from base 2 to base 10. And we apply the signal 0 this time to W minus 15. And lastly, we simply add all of these values mod to the 64. We have to make sure that these values are in binary, formatted to look good. And then finally, we have to make sure that the result is in 64 bits. And last but not least, we can create a for loop to compute all the remaining values for our message schedule. As defined by the algorithm. And at this point, if we look at the length of the message schedule, it should be 80. So I'm not gonna, of course, display the message schedule because it's a list of 80 elements, and each element is a 64-bit word, and it's not that meaningful. So we can go ahead and move on to the next part of the algorithm, which says that we need to initialize the 8 working variables that we're working with. So in every iteration, we update the 8 working variables A through H with the previous hash values that we have. And as I mentioned earlier, in SHA-512, the initial vector is defined using the 64-bit fractional part of the square root of the first 8 primes. Just to make our lives a little bit easier, because we see we have like these indices 0, 1 through 7, and they are assigned to these working variables A through H. We can create a mapping to do that easier using a dictionary approach. And I will explain what is happening shortly. And making sure that it's doing the right thing. Yeah, so the CHR command, that's the command that takes as an input a value in base 10 and returns the corresponding ASCII value. So CHR of 97 is A because the ASCII value of A is 97. And so we start from 97 and add 8 to it because we have 8 working variables, and we are mapping them to numbers from 0 all the way through 7 to match with the SHA-512 algorithm. So we have the mapping, and then we can create a new variable called register strings. Register strings, and then the 8 first primes that we have. specify in, actually here, I'm just going to write them down one by one, A, B, C, D, E, F, G, H. Look at the register strings at this point. They should correspond to the values that we previously computed. So technically these are the same values as the variable that we stored before. However, this will give us a generic approach. Let's say if we had more than one block for the SHA-512 algorithm, we need a separate variable to do this for us. Now we're done with this step. We can move on to the next part of the algorithm, which is the nested for loop. And this is how it's defined. So we see there are we're pretty much done at this point. We just need to, we have all the ingredients, we just need to maybe create a new function to compute T1 and T2 for each iteration. So let's do that. We can define a new function called T1 that takes as an input the register strings, a vector k, which is what the algorithm has defined, w, which is our message schedule, and an index, which is highlighted by the subscript letter T. We actually don't need all the register strings for computing T1. We only need E, F, and G, but we're just gonna define it. We're just gonna pass in the whole register string just in case. And using the mapping approach that we use, it allows us to map the register strings easier, as we can reference them by their corresponding letter. Now, the register strings that we have are in hexadecimal, so we need to specify the base that we're in, so that's 16. We want to compute it in base 10. And I need to do the same thing for H, E, F, and G. So 4 variable. E, F, lastly G. And then I will define a new variable lowercase k, which is just going to be the integer value of the particular iteration that we are in. Again, it is in hexadecimal, so we just have to compute its value in base 10. And lastly, lowercase w for the value of the schedule message. Message schedule in the particular iteration that we're in. Keep in mind that the message schedule values, the way that we approach it is stored as binary value, so we need to convert it from base 2, not base 16 in this case. And then lastly, we can apply the sigma 1 and the ch function. Binary of, so sigma 1 we applied on E. And then similarly, we use the ch function. and then we need to compute this value in decimal. Lastly, we have all the ingredients that we have. We just need to add them up. H plus S2 plus S3 plus K plus W in mod 2 to the 64, and we're going to return this value as such. So we can see a quick example by passing in the register strings in fraction of the 80 primes that we computed before, the message schedule, and let's say this is the 0th iteration of the first iteration. So it seems that there has been a mistake somewhere. Oh, this must have been, my apologies, this must have been 64 to 64, of course, and that looks much better. Yeah, that's the value that we get after applying computing T1 in the first iteration. And now we need to do the same thing for T2. So again, just to speed things up, we can define another function called T2. In T2, we only apply the sigma 0 to A and the majority function to A, B, and C. So first, I am going to convert this number, which is in hexadecimal form, to base 10. That will give us a number in base 10. Next, I will compute this number as a binary number. So it looks a little bit convoluted. The reason why is that Python unfortunately doesn't make it easy to go directly to hexadecimal form to binary form easily. So we just have to make that conversion first, and then we do the same thing for B and C. Again, the mapping will allow us to easily identify the variables that we are intending to work with. Lastly, I am gonna compute the application of the sigma 0, capital sigma 0 on A, and I need to convert this value to base 10 again, add this value to the application of the majority function on A, B, and C, and I need to compute this value in mod 2 to the 64. I will make sure that this time I'm putting the right values 2 and 64. There we go. And this is the value that I'm going to be returning. So just to see an application and an instance of this function, I'm just going to pass in register strings. That's all I need. And that's the output that I get. So we are very close to the end of the implementation of this nested for loop. Now we just simply need to put all of these together to simply compute this for loop. So I'm just gonna create a new function called main loop, register, just to make sure that I'm not making a grammatical mistake. Just gonna copy and paste. I'm gonna pass in register strings that we have, our vectors k and w and the index, lowercase t1, and then we apply the function t1 on actually all of these values. We're gonna pass them in. Again, this is not a very efficient implementation, but this is just for the sake of a demonstration that one can simply implement SHA-512 in Python. And then we need to convert the hexadecimal representation of the register strings into numbers in base 10. Mapping A. And we'll do that for A all the way to H. Now we need to update these values according to the algorithm. So H is assigned to G, or I should say G is assigned to H. But again, I have to make sure that these are in hexadecimal format at this point. Now we see that here we have E is equal to D plus T1, and that's what we are going to do, and what we are going to be computing. So again, the addition is done over to the 64. And then simply we are gonna assign C to D, and so on and so forth. And lastly, A is equal to T1 plus T2. So I'm gonna compute that value. And I'm gonna compute a new set of values for my register strings: B, C, D, E, F, G, H, and I'm gonna return these values. And we can see how one iteration of this function looks like. And we see that at least it makes sensible sense because for instance, if you look at the values of our register strings, we see that based off of the definition, G is being assigned to H, right? So where is G? G is this value, and this is H. Now, after the first iteration, this value should be the value for H, and we can see that if you follow it through, that the value for H is actually the previous value that G had at the start of the previous iteration. So this makes sense. And then, well, for example, for most of these entries, they are assigned from the previous values. A and E are the two values that look kind of different relative to other elements in this list. Now that we have everything together, we can put this main loop to work and run it 80 times and prepare ourselves for the next part and the last part of the SHA-512 algorithm. So let's see how we can do that. So it is important to store these values in the values of each iteration, or do not discard the values of the hash function, intermediate hash function that you work with, because you need it later on at the end of the algorithm. So I'm not gonna change the value of the hash values at the start of the of this for loop. That's why I create this new variable, and then I simply need to go over this main loop function that I define above 80 times. Main loop, and then lastly in fraction, sorry, I need to put in the message schedule and the variable I. So now I've computed some values. Let's see. So these are the values that I got at the end of the last iteration. Now let's see how we can make use of it to compute or update our hash values. So according to the SHA-512 algorithm, we can compute the intermediate hash values according to this definition. So we simply add the values that we get at the end of running the main loop that we did 80 times, which are denoted by A through H, and these ones are the previous hash values that we had. So we simply add these values together over mod 2 to the 64, compute them, and we get our new values for the new hash values, I should say. So let's see how we can compute this in Python. We take we use actually an approach using the zip function. So we see that this doesn't really make return anything readable to us. It means something to the computer, but not to the human eye. But we can put it in a list, and it makes more sense. So what's happening right now is that we can see that it puts the register strings and the value of the new register strings together, concat, as a tuple, I must say. So we have this value, which is here, and then similarly this value, which comes from the new register string here. And this will allow us to use a least comprehension approach for updating the hash values. So I'm gonna just define another function. Again, this is mainly used if you wanna have a generic approach for implementing a SHA-512 algorithm. Update register strings. So it takes 2 register strings as input. I'll define a third one, and then I will take a least comprehension approach, and I'll explain how it works in a second. So again, these values are in hexadecimal format. We need to change them to base 10 in order to be able to work with them. Yeah, that's actually fine. Add to it, and I will explain where the A and B are coming from in a second. Making sure that we format it. Now, here we need to make sure that the output is a word that is 64-bit, but we are dealing with hexadecimals. So every value in a hexadecimal string contains 4 bits of information. So in order to get to 64-bit, we simply need 16 of those. Simply, we just make sure that we have 16 bits of hexadecimal, which in turn will give us a 64-bit word. Now here is where we use the make use of the zip approach that we defined. We saw earlier. I must say, zip of string 1 and register string 2. So this will allow us to sum basically these two values, and we are taking a least comprehension approach as mentioned. Again, we simply want to return the value of this variable. That's what we do. And lastly, all we need to do is to compute, basically make the computation at this point. We have the register strings, have the new register string that can be computed at the end of the 80th iteration, and we get the following values. To make everything look a little bit nicer, we can concatenate all of these values, and that would actually be the message digest of applying SHA-512 to the initial message that we started with, which was ABC. So we did all of this work just to get to this point, and this is the message digest of the message that we started with. So pat yourself on the back for going through this tutorial, and I know it was a lot of information, but we've made it towards the end. This is the message digest that we've been working from the beginning of this video to get to this point, and we see that it is possible to implement SHA-512 in Python. And just as a sanity check, I've already included the message digest we should have gotten. Let's see if it matches. So yeah, we see that the message digest of SHA-512 it starts with DD and it ends with this string CA49F, and we can gain confidence that it is actually the implementation has been done correctly, hopefully. Now, one last thing that I wanted to bring your attention to is that we've done all of this calculation. We implemented Python ourselves in this tutorial, but there are other methods actually in Python that allows you to compute all of this without needing to implement it. So it has already been implemented in Python. We just need to use the hashlib library in Python, and let's say we want to apply the SHA-512 on this message that we have ABC, and you might be tempted to simply apply the SHA-512 at this point. You can actually just call the SHA-512 method, which is a very easy name to remember. But this will not work because our message, as I mentioned earlier, it must be a message that is in binary form of 0 and 1s. So in other words, the message string that we start with, ABC, must be encoded. Again, that's completely fine and doable. We can, in Python, we can encode a word, and there are again lots of different flavors, and this on its own will take us to a different topic on its own, which requires a lot more explanation. So there are many different ways to encode a message, but for our purposes we can use the UTF-8, and we see that it's returning something very similar to our initial variable, which is just S, so it's ABC, but we see this B here, which is a sign that it's a little bit different compared to the original variable. So now if I were to apply the same functions again to this, it's returning something. It's not returning an error, it's returning something. It's just not really meaningful to us. To make it more meaningful, we can simply use the hex digest method off of it, and voila, we get the message digest in Python using the hashlib library. And you can see here that this message digest is the same as this message digest that we got by implementing it in Python. So this will bring us to the end of this video. I hope you learned something new. Maybe you are familiar with some parts of things you've seen. Some other parts might have been new to you. Maybe you just need a refresher. I just hope at the end of the day you got to learn something new from it, and I would love to hear your comments and opinion. If you would have taken a different approach, or if you have any thoughts, I would be happy to hear. I would like to thank you for taking your time to watch this video, and until next time, bye for now.